Hi, in this video we'll go over software development lifecycle models, also known as SDLC models. So what are some of the software lifecycle activities, the activities involved in the entire software development process? So if you think of those activities, typically the very first thing that we start with is requirements elicitation. So this is where we are getting all of the requirements from the client. So that's the requirements elicitation phase. Then we take those requirements and analyze them and further understand them, and if clarification is needed, get clarification from the client. Then from there, once we have the requirements, we've analyzed it and understood it thoroughly, and that's when we move into the system design phase, wherein we come up with a high level design of the system. Then that's followed with a object design or a more detailed design. So this is the object design is more detailed, whereas the system design is a high level design. And then so after the high level and detailed design is complete, that's when we start implementation. So that's when we start writing code. So a lot happens before we actually get to coding. And all of these phases are very important to make sure that we are implementing the right thing. So then once implementation is completed, we perform testing. So that's kind of the last big activity. So basically these are the different software lifecycle activities. And basically we need some kind of a guidance on how these activities are to be organized, and that's what these models are helping us with. Now typically we'll see that during the requirements elicitation phase, so basically whatever information we get is helping us with so all of this information is gathered, so then we can begin to do modeling and begin to design the system. So the requirements help us in coming up with what's called a use case model. So this is where we are kind of thinking of the functionality and the interaction of the different functions. And then this use case model is expressed in terms of application domain objects. So that's done through a class diagram. So this is basically part of the high level system design. So we come up with a use case model and then determine the objects, the domain objects that are participating in this use case model. We create that. And then we further also structure our system into subsystems and organize it. So that's what you see over here. This is all part of the system design. And then from that application domain objects and the use case model, we then get into a solution domain object, so more detailed design. So that's also again the object design where detailed design is done, that's realized through these solution domain objects. And then finally we get to implementation, where we're actually writing source code. So as you can see, a lot is happening over here before we get to the source code stage. And then finally we have to verify the code that is written through test cases. So we write test cases in order to validate or verify our use cases, our classes, our subsystems, and the individual unit, every individual unit possible. So so basically you see that all of the activities shown here at the top are basically then used, and the artifacts produced from those activities are basically being used in the modeling, implementation, and testing of the software system. So the idea is we start out with what is the problem in the requirements analysis phase. Then once that problem is well defined, then we start thinking about what is the solution. So we come up with the system design, a high level design. And then what are the best mechanisms for implementing that solution? So that's where we think about detailed design. So here we are at the system design phase, we are mainly only thinking about the application. We are not thinking the application domain, I should say. We are not thinking about the specifics of the implementation, the platform, what kind of software, what kind of hardware. We are not getting into that. We are thinking about this design at a high level in terms of the application domain. Once that is done, then we think about the mechanisms to implement that solution, and that's where we come up with the detailed design. Then the solution is actually constructed through implementation. And then we want to now check, is the problem solved? So we test to ensure that the problem is indeed solved. Once it's solved, then can the customer use the solution? Is it ready for delivery? So it gets delivered to the customer. Once that's done, then we're into this maintenance phase where if there are any issues, the issues are fixed. If enhancements are needed, then the enhancements are are added to it, and then again delivered to the customer. So, so that's the software, the different activities in the software life cycle. And like I said, everything in the first two steps they relate purely to the application domain. We're not thinking about the solution domain yet, but then starting from the detailed design and down, what we are dealing with is the solution domain. So that's where we're thinking about the implementation details, specifics, platform, software, hardware, what kind of operating systems, what kind of browser compliance are we supposed to support for, and so on. So, what is the software lifecycle definition then? So basically, a software lifecycle is these set of activities and their relationships and how they're supporting each other in the development of that entire software system. So basically, it's these activities and in what order should they be performed. So our typical lifecycle questions are like, what activities should I select for my software project? What activities are important and should be part of that life cycle? What are the dependencies between those activities, and how do I schedule the activities? So those are the typical life cycle questions, and that leads us to these different life cycle models so that we can pick one that's suitable for our kind of project. So software development lifecycle model is basically nothing but a framework that describes these activities that are to be performed at each stage of the software development project. So we'll look at the different models that are out there, and we'll start with the most traditional one that came out. And again, we'll see that there's two kinds of two categories of models. There's linear models, which is what we started out with in the 70s and 80s, and then slowly things evolved, and then we got into more of the iterative models, and you will see that progression as I go through these different models today. So the waterfall model is the most traditional one, very easy to understand, intuitive, and based on what you just heard about the different activities that are there, we want to just perform the process. The framework is laying out the activities in a sequential manner, starting with requirements, followed by design, implementation, test, installation, and maintenance. So you see that it's a sequential one after the other. Complete requirements and move on to design. Complete design, move on to implementation, and so on. So that's called the waterfall model. So like I said, the strengths of this model is that it's easy to understand, very easy to use. The structure is such that any inexperienced staff can work with it. The milestones are well understood because completion of one phase, one activity leads to the next activity. So the milestones are well understood. It sets requirement stability because you're done with requirements and you move on into design, so which means that the requirements are set now. There's no looking back. So there's a requirement stability and no scope for change in there. So it's good for management control. It's easy to manage and track. So basically it works very well when quality is important. If cost is not an issue, if schedule is not an issue, and if when quality is very important, then waterfall works very well in those cases. Now the deficiencies of waterfall is that, as you might guess already, because that requirements happens at the very beginning, and then once that's done you move on into the other phases and there's no looking back. So all the requirements must be known upfront. They cannot be changed once you're done with the requirements analysis and you move on to the next steps. So one has to have a very clear idea of what the requirements are upfront. The deliverables that are created, so that is can be this model is good for the systems where the requirements are known upfront, but otherwise it's a disadvantage. All of the deliverables that are created in the previous phase are considered frozen. So there is no flexibility. There's no flexibility to go back and change something. It can also give a false impression of progress, because say we're done with one phase, you move on into the next, so it gives an impression of that progress is being made, but then it may not necessarily reflect that, because there could be a later phase where most of the work needs to be done, but then one might think that, oh, we have completed 3 phases of this life cycle, so we're doing good, we've made good progress, because you're not seeing the running software, so it's hard to say how much progress has been made. It does not really reflect in the problem-solving nature of software development. As we discussed in the previous videos, software engineering is more like a problem-solving activity, which means we are breaking up the problem into smaller pieces, solving the smaller pieces and putting them together. It does not really reflect that kind of a process. So in this case, integration is just one big bang at the end. Implementation, and then just put everything together at the end, and that is not easy for any significant system. Integration is one big bang as one big bang at the end is never a good idea. We run into a lot of issues with that. There's very little opportunity for customer to preview the system, because in the life cycle activities there's no scope for that, so they just have to wait until the end to be able to see anything running, and and it could be too late by the time the customer sees, and if there's some feedback, there's some issues, it's too late. All of the time has been spent and resources have been spent in coming up with it, so changing will mean more time and more money. So those are some of the big deficiencies with the waterfall model. But having said that, even with those deficiencies, there are some situations where waterfall model is a very good fit. It's a good fit where the requirements are very well known. If the product definition is stable, then it's a good idea to go with it. Where the technology is well understood and we have a sense for what technology needs to be used. Or if you're building a new version of an existing product. So there's an existing product in some legacy, using some legacy language, and you want to convert it into a more modern, using more modern technology, then the requirements are already well known, the product definition is stable, so the new version can be created using a waterfall model. It's a good fit there. Or porting an existing product to a new platform. So again, even in that situation, the waterfall model is a good fit. So then let's look at the next one, which is the V-shaped SDLC model. It's a slight variant of the waterfall with a higher focus on verification and validation of the product. So there's a more focus on quality and making sure that high quality software is produced. So in this model, we see that testing of the product is planned in parallel with along with development. So we basically in the waterfall we saw that we had each of these activities being done in a sequence, one after the other. In V-shaped, you'll see that we break it at some point and break it into a V, so that some of the steps can happen in parallel. And the steps that are happening in parallel, so as you can see, this first step is the requirements, the project requirements and planning. Now, while project planning is happening, in parallel we can plan for the production, operation and maintenance phase. So planning for the maintenance phase can happen while the requirements analysis is happening. Then the next phase is the so once the requirements have been obtained, then we're analyzing the requirements. While the requirements are being analyzed, in parallel, system and acceptance testing can be done. Then we basically go in this order, and then this way. So the third phase is the high level design. So while the high level design is being done, in parallel we can start planning for integration testing and the different test cases for the strategy for integration testing. And because the moment you have a high level design, then you have the systems and the subsystems, so you can start thinking about integration testing of how you're going to test those different subsystems. Then we have detailed design. So while the detailed design is being done, so this is where we're thinking of the individual objects and their details. So along with that, we can parallelly start planning for unit testing and writing the unit tests. This helps with test-driven development as well. We can begin writing our unit tests even before code is written. And then we can write the code to make sure those tests pass. And then finally at the bottom of the V, we have our coding. So this is the V-shaped model, and then like I said, we have taken our waterfall and then slightly changed it so that multiple things can happen. We can do things in parallel. And what we're doing in parallel on this side are testing related activities, planning for the testing and maintenance. So we discussed these different V-shaped steps. Now the strengths of the V-shaped is that because so much emphasis is on verification and validation, the strength is that we have a good quality software at the end. Every deliverable must be testable, so we are focusing on that and making sure that every deliverable is being tested. This also allows project management to track progress with clear milestones, and it's a fairly easy to use model. So those are some of the strengths of V-shaped. Now the weaknesses are that it does not handle concurrent events. So basically it's not able to handle iterations or phases. It's still a linear model. So there's no scope for going back and making changes, or so that flexibility is not there. It doesn't handle dynamic changes in the requirements. And it does not handle, there's no risk analysis activities in there. It's still just a linear model where one thing happens after the other, and pretty much the outcomes of the previous phases are frozen once that phase is complete. So that's a weakness. But having said that, V-shaped model is good for certain kind of systems that require high reliability. So it's an excellent choice for such systems. An example one would be, say, a hospital patient control application, where we want to make sure that the system has high reliability. Again, for V-shaped model, if the requirements are known upfront, then that's a good candidate for V-shaped model. And then we want to make sure that the solution and the technology are known. So this is similar to waterfall, but the additional thing with V-shaped is, if you have a system where the solution and technology are well known, all the requirements are known upfront, and in addition to that you want a high reliable software, or if it's a safety critical system where quality is of utmost importance, then V-shaped model is a very good fit for building that kind of a system. The next one we'll look at is a structured evolutionary prototyping model. So this is where developers start out by building a prototype during the requirements phase. So this is very different from the previous two in the sense that in the requirements phase itself, instead of so requirements are analyzed, but not to the extent that they're done in the previous two models. Instead, based on the requirements that are available, developers try to quickly build a prototype. And then that prototype is evaluated by the end users. So the end users then provide some corrective feedback. And then based on that feedback, developers further refine that prototype. And then they keep continuing this process until the user is satisfied. And when the user is satisfied, then that prototype code is brought up to standards and made into a final product. So that's the structured evolutionary prototyping model, very different from the previous two. Here there is interaction with the user right from the beginning, because prototypes are being developed and then they are demonstrated to the end user for feedback, and then we go through this cyclic process of getting feedback until the user is satisfied, and then that prototype is converted into the final product. So here just a preliminary project plan is developed, and then a high level paper model is created, and then quickly one gets into the prototype building phase. So when a prototype is built, it's basically just building some of the basic and critical functionality. The entire system is not built. It's just building the critical things. And then the designer builds say a database. So all of the detailed database and the detailed algorithmic functions, they get added later on. But in the prototype, only whatever is essential gets built. And then it's demonstrated, and the loop continues till the user is satisfied with that prototype. So the strengths of this model is that the customers get to see very quickly, they get to see whatever their requirements are, and the nice thing is that if requirements are not clear, then the developers can learn from the customers, and it's kind of the requirements evolve as this prototype is being built. So what we have at the end is very likely to be an accurate end product that the customer needs. Unexpected requirements can be accommodated because they're constantly building the prototype anyways, so new requirements can be accommodated. So it allows for a lot of flexibility in the entire process, and there is a steady visible sign of progress because there is something that's getting produced that can be demonstrated. So there is a visible sign of progress, and it's not just some milestones being achieved without actually seeing a system running. So the interaction with the prototype, it stimulates awareness. So if the requirements were not clear up front to the client, then basically interacting with this prototype is allowing for the customer to think about any additional functionality that might be needed. So that's again a strength of this model. But having said that, the weaknesses, it has a number of weaknesses as well. We're dealing with prototyping here, so it's basically quick code that can be just put together. So typically prototyping has this bad reputation of using quick and dirty coding methods, because the idea is not to have not to follow the best possible coding guidelines and produce the most efficient code. It's just to produce some working code. So typically the code is not well written or well designed. So the overall maintainability may be overlooked in this process. And at the end, the customer might just want the prototype delivered. Whatever they see, they might want it delivered. So the developers are in a hurry to just put together the final product. So the overall maintainability is completely overlooked in those cases, and what is produced is not maintainable software. And then there is also this risk that this cycle of producing the prototype, getting user feedback, and going back and making changes might continue forever if the customer is not satisfied. So that's a risk as well. So these are some of the weaknesses with this structured evolutionary prototyping model. But then it's a great fit where when requirements are unstable or not clear and they have to be clarified. So it helps. It helps in clarifying all of those requirements. Now, it can also be used as a requirements clarification stage of a waterfall model. So, one could mix it along with waterfall, just the first phase of the waterfall model where some structured evolutionary prototyping could be done in order to make sure that the requirements are clarified. It's a good model where user interfaces, where there's a lot of user interfaces that need to be developed, and typically in that it's a good idea to have feedback from the customer. It's also a good fit for short-lived demonstrations. So maybe a quick demonstration needs to be done for some for getting funding or some of those kind of situations, and the product is not likely to be used for very long. It's just for a short-lived demonstration. Then it's a good fit. When there is a new product that's being developed, completely new from scratch, original, one of that kind doesn't exist, then again this is a good model to start with in order to make sure all of the requirements have been clarified. It could also be used just with the analysis and design portions of object-oriented development, just during those two phases, the high-level and detailed design, in order to make sure that the requirements are well understood. So doing this structured prototyping and going back and forth with the customer will help clarify the requirements of the system. So those are some situations where it is a good fit. But then, as you saw, it still has its weaknesses. So we want to see, can we do better? Is there another model wherein there's flexibility, enough flexibility, where requirements could be changed if needed, and if it's a more reflection of the problem-solving activity that software engineering actually is. So that's where we move into more of the iterative models. And the first one in it is called the incremental SDLC. So here the idea is to construct a partial implementation of the total system. So basically build it in bits and pieces, and then slowly add more functionality as we go. That's why it's called the incremental model. And then that way we are able to prioritize and implement the most important features first. And then in subsequent releases add new functions or other functions that may not be as important. So the way this model looks is the first few steps still happen in a linear fashion. So the system feasibility, the software plan and requirements, and a high level product design are first conducted in a linear fashion, like in the waterfall. But then once the high level design is done, at that point we get into this incremental or iterative model. So once we have the high level design and with the different subsystems and their interaction, then we have the ability to break down the system into smaller parts, and then choose a part that's a priority and develop that one first. So basically after this point, when we get here, we're basically working in increments of n. So in each increment, in the first increment, we pick one module and conduct a detailed design of that module, code it, perform integration, implementation, and maintenance. So basically the idea is to completely develop that single module and make sure and deliver it to the customer so that feedback can be obtained. And then we move into the next increment, which is basically now we pick a second module or a second functionality that gets added to this existing system. We go through the same phases of detailed design, code, integration, implementation, and maintenance, and continue doing this until all of the increments or all of the functionality is implemented. So that's called the incremental model. Its strengths are that it allows for developing the high risk or major functions first, so that feedback can be obtained. And it's good that the high risk ones are developed first, so if there's some issues, then We're not spending all the money and resources into building the entire system up front. Each release is delivering an operational product. So there is an operational product at the end of every increment. The customer can use it and provide feedback on it. So it is actually using that divide and conquer technique that we discussed earlier. We're able to break down the entire development into tasks and deal with one task at a time. It lowers the initial delivery cost. Though the overall cost may not change, the initial delivery cost is reduced because we're focusing on one module or one functionality at a time. The initial product delivery is faster as well. The client gets something much faster to interact with, and then they're getting that most important functionality early on. And the risk of changing requirements is reduced. That's because if some requirements change, there is still scope to handle that in a subsequent increment. The only thing though is that the first 3 steps are still done in a linear model. So until we get to a high level design phase, until that high level design is not completed, we cannot get into the increments part. So at least that part should be clearly defined. So in terms of weaknesses, it requires good planning and design, because those first 3 steps are pretty much done in a linear fashion and there's no looking back on that. So it requires an early definition of the so we still need some sense of this complete fully functional system and how that's going to look, so we can come up with a high level design. So it allows for that high level design and allows for breaking it up into increments. So that part should be there, it should be possible. And then very well defined module interfaces can be created. Now also the system should be breakable into tasks. So that's where it's typically useful to do this on if there's a number of user interface modules, then it could be broken up into these increments easily and develop one at a time. Now the total cost of the complete system itself is not lower, it's probably still the same or maybe even more. But the initial cost, the initial delivery cost is lower because we are able to get some working product at the beginning much faster with less money. So those are some of the weaknesses. Now, having looked at both the strengths and weaknesses, this is still a good model where there's a number of risks related to either the funding, the schedule, or the program complexity. So in those cases, it might be useful to have some working product of the important functionality. If one is able to see that, then some of those risks are taken care of, and one could look for additional funding and then add more resources to it and then build the remaining features. So it's suitable where we have those kind of systems. Now most of the requirements still have to be known upfront here. They can evolve over time, that's okay. There's some flexibility, but majority of the requirements have to be known upfront. If it's important to get some basic functionality to the market early, then that's another case where this kind of a model is very good. Now projects that have lengthy development schedules, again it's a good idea to use incremental model for those, so that the customer gets to see something sooner. And then if it's a project with new technology, then that adds some risk as it is. So again, with those kind of projects as well, the incremental model is a good idea, because we can implement with that using the new technology, the most important functionality or the complex functionality can be implemented and tested and made sure that it works. So that was the incremental model. But then, as you can see, we started this discussion about risks and what happens when there's risks. So there was a need for risk analysis, and none of these previous models really supported for that, and that's when the spiral SDLC model came into picture. This adds a lot of risk analysis into these existing models. So it is an iterative one. So in a spiral fashion, in a cyclic manner, the model is repeating the same steps as in the waterfall process, but it's just that they're getting repeated every time, and in each cycle a lot of risk analysis also is being added to the process. So in the spiral process, you see that there's these 4 quadrants. Now the first quadrant focuses on so always these 4 quadrants have the same overall goal. The first quadrant, the idea is to evaluate what is to be done, what are the alternatives, identify any of the risks, and if those risks happen, what are some of the alternatives. So this analysis happens in the first quadrant. Then in the second quadrant, the next level of the product is developed, so the actual development happens. Then in the third quadrant, we start planning for the next phase. So now that we've completed this task, what's the next task that needs to be performed? And then in the fourth quadrant, we again determine the objectives, alternatives, and constraints for that next phase. So it's kind of evaluate, develop, plan, and then determine objectives of the next phase. So that's what happens in each cycle. And then, but then again, each cycle can be, the first cycle can be conceptualization, the second cycle could be requirements, then design, and then implementation. So we basically, in each cycle or each spiral, we perform certain aspect of the software development. So that's the idea with the spiral model. So like I said, in the first quadrant, determine the objectives, what are the alternatives and constraints. So basically here, so because risk analysis is a key over here in this model, we are always thinking about what are the risks in terms of functionality, what are the risks in terms of the hardware or software, what are some of the critical success factors. Now, and then we are also always constantly thinking about alternatives. What if something, if one particular platform doesn't work, what's the alternative? Do we reuse? Do we buy? Do we subcontract? Do we build something else? So, and then we're also always listing out what are the constraints in terms of cost, schedule, interfaces, etc. So that detailed analysis happens in that first spiral quadrant. And then in the second one, those alternatives are studied, the alternatives are evaluated and studied, and if there are risks, then those risks are resolved. Once that's done, then the next level product is developed. So this is where we do the typical design, review the design, develop the code, inspect the code, and then test the product. That's typical activities. But the first and the second involve more of the risk analysis related activities. Then we develop the next level product and then plan for the next phase. So come up with the project plan and the configuration and test plan and installation plan for the next phase of the spiral. And then this process continues. So as you can see, we're doing whatever we did in the previous models, but then what got added was this risk analysis. So the strength of this model is that because so much risk analysis is being done, we are able to get some early indication of some huge risks without spending too much money. That's the idea. So users are able to, they also use rapid prototyping tools in there, so users are able to see the system early on as well. And then the high risk functions are developed first. That's also another thing that's followed in the spiral model. So again, so if there is a risk, it shows up before too much money and resources are spent on it. Now the goal with the spiral, the design doesn't have to be perfect. The idea is to try out the high risk functions and see how that works. Now the users can be involved in all of the life cycle steps, because at the end of each spiral we're trying to come up with a complete functionality, so the users can be involved with that functionality and feedback can be obtained from them. Now the cumulative costs are also assessed frequently, which is another strength, because risk in terms of cost, in terms of time, in terms of resources, in terms of technology, everything is assessed. So the cumulative costs are also assessed frequently. Now the weaknesses, now one of the major weaknesses is that evaluating risks is expensive. A lot of time is spent on evaluating risks in this model, and it takes a lot of time and effort, and it might prove to be too expensive for small or low risk projects. So it's not a good fit for small or low risk projects. It's typically done for large projects, research projects that involve a lot of risk, or other kinds of large projects where some completely new kind of product is being developed, and if the market needs to be tested for it. Now the amount of time that's spent in planning and resetting objectives and doing risk analysis, sometimes it could be excessive. I mean, it could be excessive for these small or low risk projects and not worthwhile. The model itself is complex as well compared to the other models. It's harder to understand and harder to use. It needs risk assessment expertise. It cannot be done by just any regular software engineer. It needs an expertise in risk analysis and assessment. Also, the spiral may continue indefinitely, so that's another issue with it. It may never stop. So again, that's why, because of the nature of this model, it's not. I repeat that it's not a good idea for the smaller, low risk projects. The developers. The developers on the team, they might have to be reassigned. Now there are some phases, if you saw in the quadrants, there are some phases that are not related to development. They are non-development phases, and during those phases the developers don't have anything to do, so they have to be reassigned, which means they might have to be on multiple projects, and that's even hard. It's harder to manage in terms of schedule. So that's the reason I say it is a complicated model. And then it may be hard to define objectives and have verifiable milestones at the end of every spiral or every iteration. So sometimes that can be hard as well. So with all of these strengths as well as weaknesses of the spiral model, one has to pick this model very carefully, and it's a good fit when, like I said, if it's a high risk project, if it's a high-risk project and a research project, maybe then it's a good fit. When creation of a prototype is appropriate, then it's a good fit. When the costs and risk evaluation are very important, then it's a good fit. And typically, it's for those medium to high-risk projects. That's when this is used. Also, when the requirements are complex, or the users or the customers are not sure of what their needs are, or if it's a completely new product line, then those are the kind of situations when using spiral model is a good fit. The next kind of software development lifecycle models are called Agile SDLCs. These are the newer kind of models, where the idea is to speed up the process, maybe skip one or more phases in the life cycle, and maybe be less formal. We want to still have a good process, make sure a good process is followed, but then reduce the scope or reduce the amount of documentation that is to be done. So these kind of agile SDLCs, they are typically used where the product is to be developed quickly, maybe for time critical applications where the application needs to be out in the market quickly, or it's basically used for systems where it's not so important to have a very formal process. But then still have the organizations want to employ some kind of a disciplined method, and the Agile SDLCs allow for that. So some of there are a number of different Agile methods. Some of the popular ones are adaptive software development, feature-driven software development, where the focus is on defining the features and building the features, crystal clear, dynamic software development, rapid application development, Scrum, extreme programming, and rational unified process. So some of the popular ones, rapid application development is popular, where the idea is to quickly put components together and form the application. And putting the components together might also mean bringing some third-party software and putting them together. Scrum is very popular. We will look more into that in these other software engineering courses. Extreme programming, we'll discuss some of the principles of extreme programming. And then a rational unified process is it's one where the number of steps or the number of activities in the life cycle model are reduced, but it's still a very disciplined method, and it's iterative in nature to allow for good software development process. So we'll look at extreme programming for small to medium-sized teams. Basically, it's good where the software that's being developed is maybe vague at the beginning or has rapidly changing requirements. In those kind of situations, it's useful to go with this kind of a model. The key activity with this model is coding. So throughout the software project, coding is considered the key activity, and the idea is to get to coding as quickly as possible. And communication among teammates is done through code. So basically the focus is on code over here. Now, extreme programming is called extreme because there are some practices, some common sense practices that are taken to extreme levels, and it depends on the organization which of these practices are important for them. So code reviews is one of them. There's a number of them. So say if code reviews are good, then the organization believes in code reviews, then reviewing code is done all the time. It could be to the extreme that developers are doing pair programming, which is where two developers or two programmers are sitting together at one terminal and coding together. Which helps, it's basically reviewing the code all the time, because there's a second pair of eyes always looking at the code and making sure there's no issues or no bugs being introduced into the code. Similarly, if testing is considered good, then everybody will be testing all the time. So this is where the test-driven development, or you always are writing tests and then writing code to make sure those tests work. Now, if simplicity is considered good, then simplicity is taken to the extreme, where the design is kept as simple as possible. The simplest thing that works is what is used. If design is good, then everybody is designing daily and refactoring to make sure that the best possible design is obtained. If architecture is considered important, and everybody is working on that, on refining the architecture and making sure that they have that same common understanding. If integration testing is considered important, then they build and integrate several times in the day. So the continuous integration is put to an extreme, where several times, so typically it's done at the end of the day, the integration. So everything, all of the development that happened during the day is then built, regression testing is done, it's integrated, regression testing is done, and it's runnable on the server. But then if it's put to an extreme, then one might be integrating several times during the day. If short iterations are considered good, then really short, those iterations could be made really short. Typically it's a week or two. It could be reduced to hours rather than weeks. So that's where the extreme comes from. It's basically taking some of these common sense practices to an extreme level, and it depends on the organization and what they think is their principle. So typically there are 12 principles, the extreme programming practices. Planning, focusing on, and depending on which principle, they're basically focusing on that aspect. So be it planning or having small releases, metaphor, that is where all of the development is guided by this simple shared story of how this whole system works, and everyone on the team or in the organization understands that and works based off of that. Simple design, testing like we discussed, refactoring where refactoring is continuously done, pair programming, so this is like where reviewing is considered very important, collective ownership where anyone can change any code anywhere in the system. Usually that's not the case, but if an organization considers collective ownership is important, then that's how it's done. Continuous integration, 40-hour week. There are some organizations that believe that working more than 40 hours a week hampers productivity. So as a rule, none of their developers are supposed to work more than 40 hours a week. So that's one of the practices. On-site customers, so having someone from the customer team on site full-time to answer questions, that could be done and that could be useful. Coding standards, having some kind of guidelines and making sure everyone follows those guidelines is another principle. So there are these 12 practices in extreme programming. So that's one way, so one kind of agile method where some kind of a common sense practice is put to an extreme. Another one is rapid application model, where the focus is on rapidly putting together an application. If it involves using third-party software, then that's fine. It's basically gluing everything together. So in this model, again, the number of phases or activities are reduced to 4. So there's a requirements planning phase. So that's where there's some kind of a structured discussion of what the business problem is and what needs to be done. Once that's done, then get into the user description phase. So this is where one looks for any kind of automated tools that are able to capture the information that's needed from the user. So all of the tools are used to obtain information from the users in a systematic manner, and it's captured. So that's the user description phase. Then once that's done, then we get into construction phase. This is where we're actually building. So again, tools, productivity tools are used as much as possible. Code generators, screen generators, any kind of existing tools that are out there that will help in the construction phase are used. And all of this is done within a time box. So we're always operating, because it's a rapid application model, we're working within a time box. And then there's the cutover phase, which is basically the installation of the system and acceptance testing and training the users on using the system. So as you can see, the number of phases have been cut short into 4 as opposed to the 8 or 9 in V-shaped and incremental and so on. Here in this particular model, the time boxing is very critical. So getting the product out within that time is extremely important. So the strengths are that the cycle time is reduced, it improves productivity with fewer people, a lot of tools are used. So and because there's fewer people, it also means the costs are less. It's a time box approach, so it mitigates any risks related to cost and schedule. Now the customer is always involved in this model, so it's the possibility of having a higher customer satisfaction is much greater in this case. Now the focus here is not so much on documentation but on the code, and then the user modeling with the user analysis phase. The user modeling concepts are allowing for capturing all of the business information about the business, the data and the processes. That's helping in this case. But then, having said that, this model has a number of weaknesses. Here it's an accelerated development process, which means everyone on the team must be on the same page about that process and must be up for it. The goal is to give quick responses to the user, so it has to be done. But then there is also a risk of never achieving closure, so that risk is there. It is very hard to use with legacy systems. It also requires that the system can be modularized because of the use of so many different kinds of tools, and putting components together, it's important that the system can be modularized, otherwise it's hard to operate with this kind of a model. And then all of the developers as well as the customers must be committed to this rapid fire activities and ensure that a successful product is obtained at the end. So everyone on the team must be committed to it. It is hard. It is hard to work in a rapid fire environment. So it may not be a good fit for everyone. It may not be a good fit for all kinds of software. But then whenever something needs to be delivered to the market quickly, it's good for that. So when to use RAD, or Rapid Application Development, with reasonably well-known requirements where user is available throughout the life cycle. It's very important to have the user. The project, there is the ability to time box the project, and then the functionality can be delivered in increments. High performance is should not be required here, because if high performance is needed, then this is not a good model for that. It's the number of activities have been cut down. There is no activities related to software quality and testing. So it's not for high performance products. There should be low technical risks associated with the software that's being built, and the system should be such that it can be modularized. That's when RAD can be used. The next one that we'll look at is rational unified process. So in this one as well, you'll see that the number of activities has been reduced to 4 versus the 8 or 9 or 10 in the previous models. It is highly iterative, and you see that there's 4 phases: inception, elaboration, construction, and transition. And you see that there's iteration between these phases. So you go through inception, elaboration, construction, transition, and come back to inception, elaboration, construction, and transition. So there is that, and there is also iterations just within inception or within elaboration. So it allows for iterations within the phases as well, and that's great for producing good quality software. So the different phases are: inception allows for establishing and understanding the business case for the system. Elaboration is basically understanding the problem domain and the system architecture. So basically kind of further analyzing the domain and coming up with a high level design. And then this construction, which is a detailed design and then programming and testing. And then this transition, which is basically deploying the system onto its operating system. So this can be done in an iterative manner. The problem can be broken down into smaller pieces and iteratively built in these different phases. And within inception and elaboration and construction, there could be again multiple iterations. So there's both the in-phase iteration and cross-phase iteration. And so the software can be basically developed incrementally. So this RUP is a great model where it's a good mix of, so it's an agile methodology with reduced number of activities, reduced documentation, and the goal is to produce or construct code more quickly. But then at the same time, it's providing a lot of flexibility through iterations, and code can still be developed in an incremental manner. So the Scrum is another popular agile methodology, and in some of the future software engineering courses, projects will be you'll be working on projects using some of these different methodologies such as Scrum and RUP, and you'll get further exposure to it. That's all in this video. Thank you.